Rational numbers, that term you've used so far to mean fractions and decimals. Probably, that's all it meant to you. It's not just that, right? Think about number systems that you've learned over the years. The word numbers means something. If you ask someone to pick a number between 1 and 10, I want you to pick a number between 1 and 10. Pick a number between 1 and 10. Right now, don't tell me what it is. Usually when you ask someone to pick a number between 1 and 10, what do they pick? Or what? Give me an example of what they pick. 5 or 7 or 9. Does anybody pick 2 3/4? Not usually, right? You did? You picked 2 3/4 or something like it? Nobody picks 7.2 repeat, right? Nobody picks pi. Nobody picks square root of 11, right? There's a lot of different numbers you could pick, but usually people, really, if you want to be specific, you have to tell someone, pick a whole number between 1 and 10. And actually, if you say the words between 1 and 10, can you pick 1? Can you pick 10? When you say between, really, technically, what do you mean? Is 10 between 1 and 10? Not really, right? But anyways, when we talk about numbers here, there's different sets of numbers. When you first learn about numbers, when you're, 3 or 4, whatever you first learn about numbers, what are numbers to you? Like if you ask a 4-year-old, do you know your numbers? What are they going to say? Yes, I do. 1, 2, 3, 4, 5, 6. And you probably have to ask them to stop counting, right? That's what numbers are when you're 3 or 4. After a while, you add the concept of a couple different concepts. What's one concept you add? One of the first ones you add is this, the one that comes right before that. What's the one that comes right before that? The way people learn their numbers as they grow up is kind of the same in some ways as historically civilizations developed concepts of numbers. Because if you go back tens of thousands of years, this was numbers, right? Without calculators and all the math you learn and everything, you don't have much more than people could count to maybe there, but then after that you had to go get the wise person in the village who could understand these really big numbers up here, right? And certainly lots of civilizations a long time ago didn't have the concept of zero as a number. If you ask a little kid who's 3 or 4 and you say, how many elephants am I holding in my hand? They don't say, oh, 0. They say, you're not holding any elephants in your hand. Like the fact that the concept of 0 as a number is a lot tougher than the other ones, right? If you say, how many pens am I holding in my hand? And you have one there. Oh, there's 1. There's 2. They could say that when they're 3 or 4. But if you say, how many pens am I holding in my hand? At some point later on, they'll be able to say 0. It's a number 0. And then after that, you get numbers in between there. Maybe older siblings, if you have younger siblings. They learn the concept of something like a half, right? They don't necessarily know how to write it, but they know the concept of what a half means. For a young enough kid, a half, like if a half just means a part at first, like if that was a cookie, and you wanted to split a cookie with your younger sister or brother, and you did it like this, they would say, and you say, here, you get half, and I get half. And they'd say, oh, great, I got half a cookie, right? But at some point they realize that's not fair, and they realize that the concept of a half means that much, right? That it's an actual number, not just a part. And then, of course, you can get quarters and all the number, all kinds of fractional numbers. Fractions and decimals are not different numbers. I think, even I wrote it up here, fractions and decimals. They're just two different ways to write the same numbers, right? These numbers here are called counting numbers or natural numbers. When you include 0, when you include this, these are called whole numbers. What are some other numbers over here that I left out that I haven't talked about yet? Because that certainly came a lot later than the concept of 0. Let's move this over here. What are some other numbers over there? What are the numbers on this side? Negatives, right? All these negatives over here. -1, -2. The first people to suggest that you could have numbers that are below 0, that these great mathematicians or whatever who proposed this idea. Other mathematicians and stuff said, well, you're crazy. You can't have less than 0. That makes no sense at all. You're crazy. but somebody, came up with this idea, and of course, we know now there's lots of ways you can have less than 0, right? Numbers less than 0. What are some examples of ways or things where you need numbers less than 0? Temperature, right? Temperature below 0 if you use the Celsius scale. Well, if you use either one for that matter. What else? Debt, if you owe money, right? If you have less than 0 amount of money. Above or below sea level, lots of ways, right? If you include all those numbers, so if I include all of these, what are those called? Integers, right? All of those are called integers. So we got counting numbers, we got whole numbers, we have integers, and then if we include all the numbers in between, not all the numbers in between, but if we include fractions and decimal numbers, numbers you can write as a fraction, those are what are called rational numbers. Okay? There's a good picture in your textbook on page, I can't remember what page, let me just... Okay, so somewhere in section 4.4, if you can find that, there's a good picture that you can look at. One of the things you have to understand is sets of numbers. Whoops, I just passed it. There we go. Sets of numbers. I don't know if you remember doing Venn diagrams when you're in elementary school. Let me just clip a picture of this. Okay, so let's take a screenshot of this and then we can write on it. 186, is that the page? Awesome. Okay, so this is kind of like, I don't know, do you remember doing Venn diagrams? Where you had, just to remind you, before we kind of look at that, it's good if you understand or remember what a Venn diagram is. Remember Venn diagrams, things like this? You might have actually had like 2 hula hoops in kindergarten and they said, here's a bunch of shapes, and they said, put all the red things in this circle and put all the squares in that circle or whatever. And then you had to put them in one of 4 places, like in here, in here, in here, or outside the whole thing. So if this was red and this was squares, what goes in here? What goes in here? Red squares because it's inside of, this is inside of both circles, right? What goes over here? Give me an example. A red shape other than a square. Red triangle, a red circle or something. What goes over here? Maybe you guys flunked kindergarten or what? You didn't do this? What goes over here? A square that's not red, right? And what goes outside here? Not a red, not red and not a square. A blue triangle or something like that, right? This drawing right here is the same. Now you're wondering, why the heck is he telling us that? This is the same kind of thing. It's not circles, but it's the same kind of idea. The numbers we started looking at first there were what are called natural numbers, right? Natural numbers are 1, 2, 3, and so on. If you include 0, I realize that this circle includes an infinite number of numbers, and then if you add this one more, you get this huge, bigger space here. But what it's saying is, if you take all the natural numbers, if you add 0, you get the whole numbers. This set completely includes this. So it's like a Venn diagram, except that one circle is completely inside the other, right? Like if all the squares in the world were red, then this could be inside here, right? If every red thing in the world was a square, then that could be inside that circle. It's still a Venn diagram, just the circles don't overlap. Does that make sense? So that's what's happening here. Is it's a Venn diagram, but some of the circles are completely inside the other ones, right? So you have natural numbers, you have whole numbers if you include 0. And then what's the next circle or shape outside of that? What's the next thing? This, right? This box right here. And that is integers, right? It includes the other two, right? It completely includes all these. Anything that's a natural number is also all the other things, right? So it isn't that it's one or the other. It isn't like saying, if you're saying, are you Canadian or American, or are you male or female? It's not one or the other. It's like saying, are you from Vancouver or Canadian? Like, you can be both of those things. You can be a number that's a natural number is within all the other groups as well. Outside of integers is this one, right? Rational numbers. Rational numbers includes all the other ones. 0.2, 3/5, square root of 9. Why is square root of 9 a rational number? What is it equal to? 3. A rational number means you can write it as a fraction. Can you write 3 as a fraction? 3 over 1. Can you write 0.2 as a fraction? 2 over 10. The word rational number comes from the word ratio. It means you can write it as a ratio. Rational number means can be written as a ratio. Ratio of two integers. Now you notice that there's this brown space at the bottom here. Those are called irrational numbers. Now that doesn't have any overlap with the purple thing there, right? There's no overlap between here. No overlap between those two things. These numbers are not also in this group here, right? All these groups overlap up here and they're all one within the other. This is a totally separate group. Pi is an example of an irrational number. It's a decimal that doesn't repeat and doesn't terminate. So one way you could think about this is non-repeating, non-terminating decimals. Cannot be written as a fraction. Terminating decimals. Okay, that's what irrational numbers are. Pi is an irrational number. Square root of 2 is an irrational number. What does your calculator say when you look up what square root of 2 is? Somebody find out for me. Not that. Square root of 2. So it only shows that much, but it actually goes on infinitely without a pattern. There's no pattern to it. It's an irrational number. You could do cube root of something. If I do cube root of 8, is that an irrational number? Why is that not an irrational number? That's a rational number. What is it? It's 2, right? So if somebody says what are irrational numbers and you say pi and then square roots and cube roots and stuff, it's only if you're picking numbers that are not perfect cubes, right? If I put a number like 7 here, that's an irrational number, the cube root of something like that, right? Anyways, you're sort of responsible for knowing the differences between those numbers altogether. Those two groups together, the rational numbers and the irrational numbers together, are called the real numbers. Real numbers. So if somebody talks about real numbers, they mean rational or irrational. It could be either one of those things. All right? That's the first thing for section 4.4 is being able to categorize numbers like that. Can you right now then work on putting together, if you haven't written anything down now, let's flip to this. It'd be a good idea if you possibly made that drawing here somewhere, okay? Do you notice how copy the sets of numbers? You don't have to draw it the way it's drawn on that page. It doesn't have to be exactly the same. All it has to be is you have to have whole numbers. You have to have counting numbers, whole numbers, integers, rationals, all within each other, and then another one. There's actually no circles or things that overlap. They could be rectangles, circles, ovals, whatever you want. But you have to recreate that drawing here and put your own examples. Obviously, pi can be one that everybody has, but don't just copy the examples that are there. Put some examples of your own. All right? Can we try and work on that right now, please?